This is the agenda which we covered already.
Yeah, go ahead.
First topic.
So the H0 and H1 stands for the null and the alternate hypothesis. The state of the art is called the null hypothesis. You're not changing anything, so it's called the null hypothesis, whereas the contesting hypothesis is the alternate hypothesis, right? But we're going to collect data to see which of these hypotheses does the data support. But again, it's data, right? So we can collect about 30, we can collect about 50, we could collect 100,000. But the decision that we are going to make, what is the level of confidence we need to have in that decision is what this confidence that we are talking about. The typical confidence level that we talk about is like 95%, which means there's a 5% or 0.05 units variation from the normal status. And sometimes this is significant depending on the application. If we have very less data, then people typically don't go for 95%. It could be 90%, 85%, depending on the application. Right? And the significance level, we use this notation alpha to note it. It is to figure out whether the parameter is significant. It is significant if it crosses alpha. What is this parameter that we are talking about? There is something called a z-score. All we are going to do is we're going to compare the z-score with something called the z-alpha, right? So yes, we have these distributions. So I just tried testing using, can I scribble something? I'll do that when we go to the next slide, right? So the z-scores is something I'll introduce in the next slide. And all we are going to do is we are going to compare the z-score versus something called the z-alpha. And we'll try doing this with an example. And after that, you will get the quiz. Go ahead, Bharti. Yeah. So typically, we take this distribution that's shown here. It's called the normal distribution. There's nothing like an abnormal distribution. It's usually used, so it's called a normal distribution. It's also called as a Gaussian distribution. This is a bell-shaped curve. And the information that this curve hides is the area under the curve, right? So typically, when we have this is the z-score that we are talking about. It's just a normalized z-score, right? Like normalized data. So this data can correspond to anything. For instance, it could be the height of the people. It could be the weight of the people. It could be the share prices today in the US. It could be anything. But then you could just use this distribution to measure the probability content, because we normalize this data by using this formula out here, x minus mu over sigma, where x is the data point and mu is the average. Which we also call mean. In statistics, it's called the expected value. And the sigma is actually the standard deviation, which actually captures the spread of the data, right? So any data can be normalized using the z value, the z formula. As a consequence, what happens is the resulting distribution has a zero mean and unit variance. Now, there are different types of tails that we are talking about, like the tests, right? So there's a left tail, there is a right tail, there is a two tail. Typically, we might use either the right tail or the left tail, right? So the area under the curve is what it is. So if I'm going to write probability of z being less than or equal to a small z, okay? So the small z is this value that the capital Z, the cap Z takes. So the area under that is, so this is like 1 minus probability of Z being less than or equal to Z, okay? So this is essentially the probability. The area under the curve is the probability that we are measuring here. So, for instance, let's say that the claim of the pizza delivery was about 30, right? Then the different are, if you're going to get if you're going to sample like 10 delivery times, and then we get an average to be like 32. So what we do is this 30 minus 32 divided by the standard deviation from the 10 delivery times. That's what is going to be our z-score. That's how we do. So if we take the same analogy to the marketing analytics example, whatever is the claim in terms of conversion, we look at few conversions, and then we take the average. We take the difference between the claim and the average divided by the standard deviation. That's going to be the z value, right? Next slide, Bharti. Okay, I need to, that's going to be, If I delete, if I just going to send it to the recycle bin, is everything going to go off? Ah, nice. Okay, one shot. All right. So if you're able to, for a particular example, let's say my Z was like 0.4. Okay, so what it means is along the x-axis, the value is 0.4. So it's going to be, see, if you remember, this is my distribution. It has a zero mean and it has unit variance. So 0.4 is going to be somewhere here, right? So I'm interested on the area to the right side of 0.4 typically. So the Z alpha is the confidence level that we wanted to understand, right? Like what is the significance level? So in this particular case, if you take an alpha of 0.1, the corresponding Z score, meaning the probability content is 0.1, the area under the curve is 0.1, what is the corresponding Z that makes the probability content of 0.1 is the Z alpha score, 1.65. All we are going to do is we will compare the Z versus the Z alpha and make a decision. That's what is going to happen, right? So since Z is 0.4, it is here. And the Z alpha that we are talking about is like 1.65. So it's going to be further down here, like 1.6. This is 1, let's say, and 1.65 is going to be further down here, okay? So now, since Z equals 0.4 is not in the rejection region, right? So this is going to be the rejection region. Since it's not in the rejection region, we fail to reject the H naught. Now, there's a counter example here. Just in case the Z was equal to 2, then it is pretty much in the rejection region because I'm talking about 1.65 and then the Z score is somewhere here, which is at 2. Okay, so this is in the rejection region. So in that case, I reject H naught. So these are the two things. We compare Z and the Z alpha. So if the Z score is going to be in the region of failure, then we reject the H naught. If not, we fail to reject the H naught, right? Now, the point here is, I just took 10 samples or I took 20 samples. What if I had taken some other 20 samples? So there is a chance that the results could have changed. Now, what is the probability of being wrong in the decision that we are making as fail to reject or reject H naught, just because the samples changed? So that's called the p-value. Right. Now, how do we do this? A very simple application in the sense an implementation is provided here, right? So the P is the question is, what is the probability that the Z that we computed is greater than 2? Because we computed it to be 2, what is the probability that it was greater than 2, right? So the probability of Z being greater than 2 is 0.023. This can be obtained from any graphs, meaning the standard normal plots, or from a spreadsheet formula. And this is less than 0.1. This 0.1 comes from the alpha value that we are talking about. Now, in this case, we will reject H naught because there is no enough evidence that the value that we obtain is by chance. It is like really far away truly. But just in case the p-value that we computed was greater than 0.1, then there's a chance that, by chance we made that decision. So we won't, the p is not significant in that case, but in this particular case, the p is significant. So finally, just one thing, if this is slightly confusing, all you need to do is find out what is the probability of your Z being greater than the Z value that you took, the Z score, and compare that value with our alpha, okay? And if it's less, then your P is significant. You are fine with the decision that you made. If it is not, then the P is not significant. That's all. With this, I guess we will get into the quiz. Is that right, Bharati?
Yes, we'll look at the template to answer the question, and then
Yeah. So this is the theory, but she's going to show you a spreadsheet with some data, and then she will go. Okay, the next one that we're going to talk about is the difference in difference. This is about counterfactual. As the name suggests, this is the counter of the factual, right? So the factual is there is a time series or a time strand or a particular set of people are exposed to the ad campaign and they have reacted in a particular way. But just in case, if we did not expose those set of people to the ad campaign, what would have happened? That is the counterfactual. Once we have subjected them to the ad, what we have is the factual, but just in case, we cannot go and undo that, right? If we don't expose them to the ad, what would have happened is the counterfactual stuff. We always need the counterfactual. We have the factual. If we sort of figure out what the counterfactual is, and the difference is what we measure using different metrics as increment, lift, whatever that is, right? So now, for instance, different regression approaches, the geo-based regression or the time-based regression, these are part of the lecture handouts that were given to you. What we want to do is here are two conditions here. This is the pre-experiment and the post-experiment. There are two situations in the test and the control, right? So the test, they started here, and then the test in the post experiment was here, whereas in the control, it started here and then it went here. Now, the question is, I want to know, just in case if I didn't expose the group of people in the test to the ad, what would have happened in the post? I don't know, I mean, maybe it would have been the same, similar to the control. So, it could have been more or less the same slope. So it's very likely that we might have something here. That's what we show here. And that's essentially called the difference in difference, right? The effect of campaign difference in difference is accounting for the differences in the test and the control versus the general time trend. Now, the way that I call this is the intra-difference one, meaning the intra-difference is the difference in the test. There's no inter-differences between the test and the control. Intra-difference is pre minus the post in the test, and there is a pre minus post in the control. And then you take the difference between them. That's going to be the difference in difference. And that's probably the way that it came, difference in difference, right? So there are two different. So DTW stands for dynamic time warping. It's not like a sci-fi movie or anything. I saw a post on LinkedIn. So this is about, we want to compare like two time signals. That's primarily the idea oftentimes when we want to do, we want to understand if there is an effect on the campaign, right? Like what if there was no campaign, then there is a time strand. And if I had an ad campaign, then there is a time strand. I might want to compare those two. So one of the techniques, that there are like several techniques by which we can compare two different time signals. One of the ways that we can compare is the dynamic time warping. The interesting point of dynamic time warping is it does not depend on the window size. And the other thing is it could, it doesn't matter on the frequency in which we sample. There could have been a situation where you took like several samples in a particular time window, and you took few samples in the same time window elsewhere, but you still will be able to compare the two time signals, right? So here, we might not have as much time to get into the details of this. So if you look at it, so the way that we compare is like we take time instances in each time signal, and then we compare it, right? So for instance, if you take this particular picture on the right bottom, is so if you see on the top time strand, I'm like mapping one time instant to like 4 time instants here, right? So if I were, imagine that if I'm moving this to the right, then this kind of like a V kind of a structure is going to like even out, and then we might end up having a time signal like this, right? So this would have been the case provided the sampling frequency was the same between the two signals, right? But what DTW does is it takes this information, the frequency information, and then it measures the DTW. Can you go to the next slide, Bharati? Oh, okay, sorry. Yeah. So a quick visual analysis, this is to show how we can be misled if you're going to compare two time signal visually, right? So here is the two pre-experiment and post-experimental graphs here. So you've taken this is one set of data. So just remember this, go to the next slide, Bharati. Okay, this is visual 2. There is like a valley, there is a peak, there is a valley. Similarly, there is it sort of follows, right? The pre-experiment and the post-experiment. Okay, so one, in this case, both says pre-experiment, maybe control and test. Okay, all right, Bharati, next slide. So these are like different situations. Okay, so there is an experiment, pre-experiment, and a post-experiment situation, let's say. So there is a valley, there is a valley, there is a peak, there is a peak, there is a valley, there is a valley. Obviously, I'm trying to lead you to the wrong answer. So that's why I'm showing you all those things, right? But the whole point is you need to compare these graphs. All right, next slide. Okay, fine. All right. So you have these three graphs here. And if we were to compare these three, which one would you say is the closest? I mean, which one had identical graphs of blue and red? It's going to be a very close catch, right? They all almost look identical. So if you look at it, it sort of like follows this curve and comes down. This again follows the blue curve and comes down, right? So that's where math actually helps. Math like DTW helps. And for here, but in this particular case, we have these scores. But how do we make a decision? The lower DTW scores indicates a higher similarity between two time signals. So in this particular case, which was the best thing? Is that the quiz question, Bharati? No, right? No, that's not the correct. Okay. So in this particular case, the second visual was the best combination. Okay. All right.